The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
I'd like to introduce the first speaker here, Dr. David Sanders from the University of Nevada, Reno. And the title of the presentation is the use of post-tensioning and pre-tensioning in columns to mitigate earthquake damage.
Well, thank you. I'd like to welcome you all to Reno. Anyway, what I wanted to talk to you today about was a series of projects that we've been working on where we've been looking at ways to mitigate damage in earthquakes. I think at the beginning, when we started doing research on the seismic design of columns, our focus was just on life safety. How can we get these columns to stand up? How can we get bridges to stand up? But we've realized that these earthquakes are extremely expensive. So now our focus is shifting from life safety to mitigating damage. This work that I'm going to show you today is a series of projects that have a lot of people that are involved, certainly graduate students that are listed here, also professors from different institutions. My colleague, Saeed Saidi, was a PI on one of the projects that I'm going to show you today, and I was a co-investigator on that project. A project I'm also going to show you is a cooperative project between the University of Nevada and the University of Washington with John Stanton and Mark Eberhardt. And also just a couple of slides on another project that I did cooperatively with Paul Zeal from the University of South Carolina. So what are the benefits of post-tensioning? Well, we know that it has recentering capabilities. We know that it can reduce the amount of damage that are in the system. We know that with unbonded post-tensioning tendons have shown a reduction in residual displacements, that we can pull that column back into place. And also the other thing is that localized inelastic straining can be avoided because our straining is being distributed over a length instead of being concentrated over a very short distance. And this helps us out tremendously. Some of the issues that we have to be concerned about is that we have an initial pre-stressed force that must be carefully selected because we don't want these tendons to be yielded. We want them to stay elastic during the large earthquake event. Replacing these tendons is not easy, and that's certainly one of the drawbacks of the system is how do we go about replacing these tendons if we need to take them out. Previous work anchored the tendons in the base of the footing, making it nearly impossible to gain access and to replace them after an earthquake. And in one of the experiments, we're looking at ways to maybe potentially alter the path so that we can get these tendons out if we need to. And one of the more haunting problems, and our studies don't necessarily address this yet completely, but long-term durability is a concern with these unbonded tendons. If the column becomes cracked and we can get chlorides into that system, what happens with these tendons? Now, it helps the fact that the system is compressed under a dead load, which is certainly different than what you would find in a beam or a typical cold construction joint in a beam. But there's still issues relative to this long-term durability. So one of the first tests that I was involved in was a segmental project where we were looking at post-tensioning this system together. It was just a series of blocks that were stacked on top of each other. This is the actual test specimens up here on the top. And one of the things I wanted to point out with this particular experiment was that there was no reinforcement crossing this bottom joint. So this truly was a only post-tension system. When we look at this system, it actually performed extremely well. You can see that even at large displacements, we had no residual displacement on the system. This was a shake table test that we did at our facility here at the University of Nevada, Reno. We're giving a tour of that facility right now. So if you want to try to find another time to go over there, we could try to arrange that. But what was interesting about this is that since all the strength was coming from the post-tensioning, at the end of the test, there was a fair amount of damage that was down here at the bottom, but that's all cosmetic. There's no buckling of reinforcement. There's no yielding of any reinforcement because all that's crossing the joint is the post-tensioning. So to me, this is an extremely viable system all by itself. But the issue is, of course, energy dissipation. How do you dissipate energy? But if you can dissipate that energy through another mechanism, maybe through a combination of a base isolator or some other slider or something else in the system, you don't have to do that in the column. Therefore, after the event, you've got this recentering capability and you've got damage that's very easily repaired. Another project that we did, this one was funded by the Nevada Department of Transportation, and in this one we took that idea of the post-tensioning, but we started to look at actually having reinforcement cross the joint. So in that we looked at two different longitudinal reinforcement ratios. Again, this is post-tensioning in combination with conventional reinforcement. We kept the transverse reinforcement about the same as 1%. And what we also did that was a little bit different than other people have done is they've tended to concentrate all the tendon force in one location in the middle, which is fine when you're dealing with a scaled column, but if you're actually looking at a real full-size prototype, you're not going to be able to put all the reinforcement right here in the middle, the post-tensioning in the middle. And so we looked at the case of spreading out that post-tensioning out here in the boundary. And of course, that's going to alter the behavior of that post-tensioning. We also looked at what do we do with this post-tensioning when it gets down to the bottom. Again, most of the other experiments just anchored it right down here at the bottom, which essentially makes it impossible to replace. And we flared this out to the sides and in order to be able to actually access the tendons after the event. So this is a picture of that. It's a relatively complex issue of bringing the tendon down and then flaring it out to the outside boundary. Another thing that we did is that the tendons that we used were actually coated in plastic with grease in them. So again, trying to add a layer of protection. So it's not just typical post-tensioning strand or a duodag bar. It's actual strand that's coated with grease with the plastic sheath. So this would be the same thing that you would use in a slab. Okay, so we're actually increasing the protection over this slab. And we found that when we took these tendons out at the end of the experiment, and we really pushed these tests extremely far, that there was a little bit of damage that occurred on that outside plastic sheath, but it wasn't penetrated all the way through. And this is after a large number of cycles. The way this was tested was using a slow cyclic method. So we went through increasing levels of displacement and went up to a maximum of 10% drift. So as I mentioned, there were two different levels of reinforcement. There was a low level of longitudinal reinforcement. The amount of post-tensioning stayed the same, but the amount of conventional reinforcement that was crossing the interface at the base of the column was changed. And we can see that in this system we were getting out to 6 and 7% drift before the system became altered, okay, or the capacity was reduced. And so we saw a very good behavior in terms of the overall system. You'll also notice that this is load versus displacement. That's not coming back through the center. And it's not coming back through the center because we have a combination of conventional reinforcement and post-tensioning. What was also interesting about this is that these two graphs on the right are showing the strain in the tendon versus the drift. So if we look at this picture over here in the corner, this is that configuration of 1, 2, 3, 4 post-tensioning systems that we have, or tendons. The system is being pushed in this horizontal direction. So 2 and 4 are kind of you might say, near the neutral axis or about the axis of bending, and 1 and 1 and 3 are the ones that are more extreme. So if we look at 2 and 4, they had a strain pattern that looked like this because the neutral axis is moving back and forth across the system. And in the contrast, if we look at 1 and 3, they have a pattern that looks like this. Okay, so when the system is in compression, the strands are still in compression, but they're much lower versus when they're out being pushed at the far end, they're having a large tension sorry, I should say large tension in them. But what's important is that the yield is around 8,600 microstrain, and that we're staying below that 8,600 even at 10% drift. Okay, so we're maintaining that policy of not having the strands yield. When we go to look at the high case, okay, this is having a higher level of conventional reinforcement crossing the joint. Again, we've gotten very good performance. In this case, you're not getting much of a reduction out to about 9%. This is displacement. The drift is it's 1-to-1 essentially. So 7% drift is 7.56 inches of displacement. So we're at 8 and 9% drift. Again, we're getting very good displacement properties. Again, though, this is not coming back through zero, all right? And it's, again, because of that conventional reinforcement. Right? We see the same patterns that we had before. These are the ones that are kind of about the axis of bending. This one is the ones that are out here at a little bit more larger distance away from the center. But again, we found the case where we were not yielding the tendons. So in conclusion, both of these reinforcements, or both of these patterns, in fact, if you go back to the first one where we didn't have any conventional reinforcement, all of them provide a certain amount of recentering capability. Okay? The amount of recentering that occurs is really directly a function of the amount of conventional reinforcement that you're putting in there. And so it's, you as a designer have a choice in terms of how much of that you put in. The tendons didn't yield even out to 10% drift, and so we felt very good about that because that was one of our primary concerns. And again, when we have this recentering, the residual displacements were slightly higher when we had a higher amount of traditional reinforcement. So essentially 3 inches versus 4 inches as we increased the amount of conventional reinforcement. When we had those tendons exiting out the side, the system still behaved fine. There was no impact of that. And they had similar damage. The low reinforcement showed slightly more than the higher one, but it was really difficult to tell in terms of an overall performance difference. Well, if we take that same principle that I showed you in the first slide, where we had a segmental joint, this is conventional precast system with a series of series of segments that are up the column. This opens up some other opportunities. And this is the project that I mentioned that I did with Saeed Saidi, my colleague, where what we can do is we can start to look at what we're doing in this bottom segment. Okay, maybe there's some different things that we can do. Maybe we can use different materials. Maybe we can use in that different reinforcement, or maybe even different concrete or different confinement ratios. We can also look at maybe what the height of this pedestal should be. Maybe it could be, in one case that we've looked at before, essentially there wasn't a pedestal, but maybe we can shift this up. And what this does is it allows us to have an interface here that we feel is more like what we're used to, right? We're not having a cold joint here. We're having our traditional reinforcement that's fully developed. So as I said, this opens up some opportunities to utilize some materials that are more expensive. Okay, we can't afford to use them throughout a structure, but maybe we can use them in this isolated area where they could be most effective. So there's ECC, engineered cementitious composites. These things are incredibly ductile, amazingly so, and provide us with the ability to reduce the amount of spalling that's in the system and hold the system together better. Fiber reinforced polymers. We've used these extensively in retrofitting, but maybe we can use them as part of traditional construction by applying them in these areas where we think that they could be most effective. And then maybe we can put some sort of elastomer in this system. What can we do in order to, again, introduce some flexibility and mitigate the amount of damage that's occurring in the system? So this is the construction of those columns. We went back to the single column here or the single post-tensioning in the middle of that system. If you look over here on the left, you can see that this is the footing, and this is the reinforcement that's extending up through the footing and creating this kind of pedestal method where we can, again, exchange that out. Or you could actually make this as a segment if you wanted to, but in here we're trying to investigate the reinforcement behavior. And then this is a picture of them actually constructing the specimen. So let's look at some of these options. The first one I wanted to show you was this elastomeric bearing. In this one, there was some work that was done in Japan in which they actually put an elastomer right in line with the column. And so we extended that concept in which we took that elastomer, and this is what it looks like here, but we put in steel shims to make the elastomer stronger. They had some issues with the elastomer down in the base of the column. By putting some steel shims in there, we were able to strengthen up that elastomer and help it to perform better. And you can see the reinforcing column cage here with the elastomer stuck right in the middle. Another choice is, this is the first one. Before we got to that, we did a conventional or benchmark test. So this is just using traditional materials that you would have so that we could compare that with the other cases. Right? So this is the first one here. The base segment used the combination of the rubber pad and the concrete, like I said. So this is that rubber pad. Here's the column made out of conventional reinforcement. Our hope in doing this is to minimize the damage in the system and increase energy dissipation. The next one that we did was one where we looked at the base of this column and using an FRP, or the fiber reinforced polymer. The base segment and the second segment were wrapped in the FRP. Again, the dissipation of energy by yielding of the longitudinal bars at the base segment. The idea was to concentrate the damage in that base segment. Again, improving the concrete strength by wrapping it in a fiber reinforced polymer, minimize the damage, and improve the concrete ductility. And then this last one here was using the ECC. Again, looking at it in a targeted way. The base segment and the segment were made out of that ECC material. And again, the same objectives: improving ductility, minimizing damage, and increasing energy dissipation. Okay, so how did we test these? Okay, so there's the conventional benchmark, and then there's the FRP, and then there's also the ECC. Again, we use this with our shake table facility that we have at the University of Nevada. The way that this works is that the table is under here, underneath the specimen itself. We take the inertia mass, and we take it off the table and put it on this mass rig. This mass rig is an unstable structure. It only receives its lateral stability from the column itself. So as the table moves back and forth, this mass moves back and forth. Again, that's the inertia mass that would come from the bridge. The problem with moving it off is now it doesn't provide you with the axial load that you need in your system, and so we have vertical rams here that provide that axial load. So let me show you a video. This is the video of the one with the, if I can get this mouse to. So again, it shows you that rotation. It's essentially inducing it like a base isolator, but it's in line with the system and helps to mitigate the damage. Now, of course, what I've done is I've gone to the extreme event, or the higher level of events. This is at 1.5 times Silmar. The Silmar record is out of the 1994 Northridge earthquake, and we see that we haven't completely prevented damage from occurring at an earthquake that, again, was 1.5 times what happened. But this shows the different one. This is the base experiment, okay, the benchmark. This is the one with, I think this is ECC, the fiber reinforced, and you can see that the amount of damage here is substantially less than what we had up in this case. If we look at the load displacement curves of each one of these, okay, this is the rubber SBR1, so this is SBR1 versus the conventional case, okay? So the SBR1, the initial stiffness is a little bit less, but it doesn't have this drop-off that we saw with the conventional case. This is the ECC versus the conventional case, and we see that the ECC is the green line, and again, it's not showing that same drop-off, but they're relatively close, but not seeing the same drop-off that we saw in the conventional case. And this is the case with the fiber reinforcement around the sides. This is the blue line. It's the one that's up here. So not only do we see an increase in overall capacity, but we also saw, again, not the same amount of reduction that we saw before, right? So if we look at the energy dissipation that's occurring in these, if we go back and look at the curves from our hysteretic behavior, again, the SC is the conventional case, and then we have the rubber and the fiber and the ECC that the amount of energy dissipation that we're getting in these cases is increased. Okay, so that's a good thing for us in terms of the overall behavior of our system. Now this is just a comparison of all the curves to try to put them on here. This is the conventional, and this is our analytical model, but this is the conventional case, this is the rubber case, the fiber, and the ECC. And again, you see all of them have these large curves because there are damage that's occurring later on in the cycle. But if you look at early on, you can see that this is much more compact than the conventional case when we were looking at the rubber case. And these other two cases with the fiber reinforced and the ECC, we are getting degradation, but again, the amount of energy dissipation that we're getting out of these cases is substantially more. Okay, so what's the conclusion that can come out of this? Well, the plastic hinging incorporating the advanced materials experienced, now it says the word minimum damage here, but that was at lower levels, not at these maximum levels. The residual displacements were less, okay? The energy dissipation in the innovative details were larger, okay? And we saw just overall better performance out of these systems. Now, I just threw this in a slide. This is another project that we did. This is the one with the University of South Carolina. What I find interesting about this is that they've just taken piles that come up out of the ground, and they've taken a cap beam, and they just cast it around the piles. Okay? There's nothing that connects the piles to the cap beam other than the pile themselves. There's nothing else there. There's no reinforcement that extends out of the piles. There's nothing other than the pile itself with the cap beam. And this was a relatively large scale. The piles were actually cast in South Carolina and shipped to us. And then we just racked this frame back and forth in order to study its overall behavior. I don't have time to go into a lot of detail on this one, but we saw that the pile itself stayed fully connected with the cap beam. It never separated from the cap beam. And we did see some cracks that were opening up at this interface. This is at 0.5 of the design level, this is at the design level, and this is at 2 times the design level earthquake. So obviously we have a large crack here, but we had overall very good performance even though the thing was just stuck into the cap beam. This is a project that we're just now working on with the University of Washington, and this is another hybrid system. And I think the theme through all of these is trying to bring different ideas together to try to maximize the performance. So if I take a moment and look at this, what this is, these are pre-tension columns. And again, it's an example where we've taken a project and the columns were actually made at the University of Washington. They arrived at our institution just at the end of last week. So they're pre-tensioned, but they're pre-tensioned and unbonded, so a little bit different combination. You can see that at the ends of these columns, they are pre-tensioned. But in this portion of the member where there's kind of that white around the green, this is an example where these are unbonded. So the tendons are bonded here and then unbonded along their length. So it's an interesting combination of the fact that you get the advantage of being able to make these in advance. You get the advantage that they're pre-tensioned, okay? They have an active axial force on them, but you don't have the problem in the previous case where you had those concentrated strains and a large crack occurring because the system wasn't unbonded. So in this case, the post-tensioning is unbonded. Well, if it's good for pre-tensioning and post-tensioning, it should be good for conventional reinforcement. So the conventional reinforcement also crosses this interface. And in that area, we're also unbonding part of the conventional reinforcement. So there's unbonding in the pre-tensioning reinforcement and unbonding in the traditional reinforcement. So when these specimens show up at our facility, we're casting the footing. This is traditional cast-in-place concrete for the footing. And then in this case, we're actually pre-casting the cap beam also. So the system is put together, which makes it also effective for accelerated bridge construction. If I go through these slides, this picture here is for the strand, this picture here is for the rebar, and then we have the overall behavior. So as you're moving yourself out, the strand moves out and comes back, whereas the traditional reinforcement is getting that hysteretic behavior. The end result is you end up with something that looks like this. So it has a combination of both energy dissipation, and very small residual displacements. So they did some single column tests up at the University of Washington, and again you see that behavior with very small residual displacements. So if you come back to our lab in a few months, what you'll see is this test setup here. This is the same one that we used several years ago with conventional columns, but now we'll be using this system in order to test it on our three-shake table system. This is the type of damage that we saw last time in the conventional case, and hopefully I can show you next time that there's very little damage using these new details. And with that, I thank you for your time and your attention. Yeah, thank you.